There's this really fascinating paradox built right into human nature when it comes to engineering.
Oh, absolutely.
Like when we build a highly complex system, whether that's a massive logistics network or, a huge piece of enterprise software, our ultimate goal is perfection.
Right, you want it to be flawless.
Exactly. We want to finalize the architecture,
Yeah.
deploy the code, step back, and just admire the quiet stability of what we've built. The instinct is to basically declare it finished, safe, and totally unbreakable.
Yeah, you put a bow on it.
Right. But the paradox is, to definitively prove that a system is unbreakable, you can't just leave it alone and hope for the best. You actually have to actively, intentionally try to break it.
I mean, it's entirely counterintuitive to traditional engineering mindsets. For decades, the prevailing philosophy in software development was just engineer for stability, right?
Yeah.
Protect the system at all costs.
Build the walls as high as you can.
Exactly. Build walls, lock down permissions, treat the whole production environment like a museum exhibit, basically. But the problem with treating your infrastructure like a museum exhibit is that it never tells you what happens when the building's foundation actually shifts.
Which brings us perfectly to the mission for today's deep dive. We are exploring the counterintuitive, slightly terrifying, but absolutely essential world of chaos engineering.
Such a great topic.
It really is. And we're pulling from this really interesting article by Aaron Rose published on tech-reader.blog. It's titled The Secret Life of Azure, the Chaos Monkey.
Yeah.
And Rose uses this fictional narrative to unpack a very real technical challenge, which is how do top-tier software engineers working in environments like Azure AI and LLM ops build systems that don't just look resilient on an architecture diagram, but can actually survive a cascading failure out in the real world.
And, the narrative format Rose uses is highly effective. It takes all the abstract mechanics of cloud infrastructure and, well, it grounds them in human psychology.
Yeah, totally.
It illustrates the fundamental difference between hoping your system works because you designed it well and knowing your system works because you've literally watched it survive an attack.
Okay, let's unpack this, because Rose sets the scene in a location you would not normally associate with cutting-edge cloud computing.
No, not at all.
He places us inside a grand Victorian library in London.
I love that choice.
It's so vivid, right? He describes it as an environment where code quality is the unspoken objective and craftsmanship is the absolute priority. You can just picture the heavy oak tables, the meticulous organization, the hushed silence.
Very dark academia.
Yeah, exactly. And in this library, we are introduced to two main characters. We have Margaret, who is this seasoned senior software engineer who has clearly survived her fair share of system outages.
She's seen some things.
Oh, definitely. And then we have Timothy, her junior colleague, who is currently riding high on this wave of absolute confidence in their latest deployment.
And that Victorian library setting is such a deliberate choice by the author. It evokes a sense of permanence and absolute order. It's a place where everything is perfectly categorized and predictably quiet.
Right.
And that physical environment mirrors exactly how Timothy perceives the digital architecture they've just deployed. He views their software as a finished, static monument.
And the text highlights that their newly deployed system is running flawlessly. Like their model ladder is polished, their circuit breakers are primed.
He's feeling good.
Yeah, Timothy is leaning back in his chair, admiring what Rose describes as the cobalt blue steady state of the dashboard. Everything is totally calm. He actually looks at Margaret and says, "It's rock solid. We've accounted for every failure. The fallback is ready. We're untouchable."
He is experiencing the absolute pinnacle of engineering pride right there.
Oh, for sure.
But he's looking at his perfectly quiet dashboard and making a fundamental error. He is mistaking silence for safety.
Wow.
Margaret, on the other hand, she possesses the skepticism of a veteran. She doesn't smile. She doesn't share his relief at all. Because she understands that a quiet dashboard during a period of low traffic tells you absolutely nothing about how that system will behave under massive, unpredictable duress.
Right, and Margaret responds by picking up a cobalt blue marker, which is the exact color of that peaceful dashboard, by the way.
Such a great detail.
Yeah, and she draws a small, mischievous-looking monkey holding a pair of wire cutters right on the whiteboard. Then she delivers what I think is just the most impactful line in the entire article. She says, "Confidence is the most dangerous state in engineering, Timothy."
That statement serves as the thesis for everything that follows. I mean, why is confidence so dangerous?
Because it breeds complacency.
Exactly. Unearned confidence breeds complacency. Timothy assumes the system's architectural fallbacks will hold simply because, well, he was the one who wrote the logic for them.
Right.
He's looked at the blueprints, he's reviewed the code, and mathematically proved to himself that the system is safe.
But, like, reviewing the logic is definitely not the same as experiencing the stress.
No.
It actually makes me think of martial arts. You can be someone who has flawlessly memorized every form and kata in your living room. You have perfect form doing high kicks in front of a mirror.
Right.
You possess what Margaret brilliantly terms theoretical resilience. But until you step into a ring, spar with a live opponent, and actually take a punch to the jaw, you do not have validated survival. And Timothy has never seen their code take a punch.
That sparring analogy captures the dynamic perfectly. Memorizing the forms is basically equivalent to engineering the fallbacks, writing the try-catch blocks, deploying the circuit breakers.
Right.
Sparring is chaos engineering. Margaret is telling Timothy that to truly trust the system they just built, they need the Chaos Monkey. They have to force the system to defend itself.
Which, okay, if I am Timothy in this scenario, my hand is hovering right over the emergency brake.
Oh, absolutely.
I mean, Margaret is essentially proposing that they actively attack a live production system. So I have to challenge this logic for a second. Why is this even necessary? Why can't they just run these stress tests in a staging environment? Staging is literally built for testing.
It's the logical alternative, right?
Yeah. Simulating an Azure outage in production with live users just seems inherently reckless. Like, what if this digital monkey corrupts the scholar's research or something?
And that is the most common pushback against chaos engineering, and honestly, it's a completely valid fear. But staging environments are essentially clean rooms.
Okay.
They lack the entropy of production. You can simulate traffic in staging, sure, but you cannot perfectly simulate the bizarre, unpredictable ways real users actually behave, or the microscopic network latencies that only ever occur when a system is under genuine organic load.
So it's like testing in a vacuum.
Exactly. Margaret knows that testing and staging only proves that the system works in a laboratory. She needs to know it works in the wild. But here's the key. She is not being reckless. What's fascinating here is how she redefines the concept entirely. She draws a circle around the monkey on the whiteboard, and she calls that circle the cage.
Right, and this is where we get into the concept of a controlled burn, which I love. In forestry, you don't just wait for a random lightning strike to ignite a massive wildfire during the peak of a dry summer.
Right, that would be a disaster.
Yeah. Instead, you intentionally start a small, highly managed fire. You dig fire lines, you pick a day with zero wind, and you burn away the dry brush on your own terms.
Precisely. Margaret explains that they cannot afford to wait for Azure to experience a massive infrastructure hiccup at, say, 3 a.m. on a Sunday.
When everyone is asleep.
Yeah, the engineering team is asleep, response times are slow, panic sets in, it's a nightmare. By triggering the failure intentionally during regular hours, when the entire team is actively monitoring the dashboards and ready to intervene, they maintain total control over the variables.
And the text mentions that the monkey's job is to randomly disconnect the lead planner or throttle the network. To prevent that from becoming a full-blown catastrophe, Rose outlines the specific safety parameters of Margaret's cage.
Right.
And the first parameter is the blast radius.
Yes, the blast radius defines the absolute maximum scope of the experiment. Margaret restricts the monkey's access to exactly 1% of non-critical traffic.
Okay, so it's tiny.
Very tiny. By doing this, she ensures that even if the absolute worst-case scenario unfolds, like if the monkey breaks the system and the architectural fallbacks completely fail to catch the error, 99% of their users won't experience a single interruption.
That makes a lot of sense.
The potential damage is contained to a mathematically manageable subset.
Okay, so that addresses the scope, but it doesn't really address Timothy's fear of corrupted data. If the monkey is in production, how do they guarantee it doesn't just, permanently delete a database or overwrite a user's file?
Well, that is handled by the second parameter of the cage, which is read-only chaos.
Okay.
Margaret explicitly assures Timothy that the Chaos Monkey is structurally isolated from user data. It never has permissions to touch the right paths, which are the channels where new information is saved or modified in the database.
So it can't change anything.
Right. Its mandate is strictly limited to attacking the infrastructure. It severs network connections, blocks API calls, takes servers offline. It attacked the roads, not the cargo.
The roads, not the cargo. That is such a vital distinction. And there's one final safety net, which is the kill switch.
The big red button.
Literally. Margaret describes an automated failsafe, a big red button that halts the experiment instantly. If the latency spikes beyond a critical threshold, or if that blast radius begins to expand beyond the 1%, the switch automatically terminates the monkey's processes and reverts the system back to its steady state. As Rose puts it in the text, we prove the resilience in a cage before we trust it in the wild.
It represents a deeply sophisticated defense in-depth strategy. You have the blast radius limiting the scope of the impact, the read-only constraint limiting the type of damage, and the kill switch limiting the duration of the incident.
It's like wearing a belt and suspenders.
And carrying extra rope, yeah. When you combine those three elements, you completely de-risk the process of intentional failure. You extract the intelligence of the failure without suffering the consequences.
Okay, so we've established the monkey, the cage, and all the safety parameters.
Mm-hmm.
But the logistics of execution are just as strict, right? You don't just randomly unleash this script on a Tuesday afternoon without telling anyone.
Definitely.
Margaret draws a lock on the whiteboard cage and specifies approved engineers only, which introduces the concept of the game day.
Right. A game day is essentially the operationalization of chaos engineering. It's a scheduled, highly supervised, heavily documented event.
Like a fire drill.
Exactly like a fire drill. You gather the relevant engineering teams, everyone is briefed on the exact parameters of the experiment, and you treat the event with the same rigor and preparation you would apply to a major product launch.
Which introduces a really crucial element of the scientific method here. You can't just break a component and passively observe the wreckage. You have to define exactly what you expect the system's self-healing mechanisms to actually do.
Yes.
Rose details that every game day requires a signed-off plan and a steady-state hypothesis.
And this raises an important question, right? How do you define success in a failure? The steady-state hypothesis is the metric against which the entire experiment is judged. Let's look at the specific example Margaret uses in the text. Her hypothesis is, even if the lead planner vanishes, the user should receive a valid response within 3 seconds with 99.9% accuracy.
We should probably break down the technical architecture behind that statement, because lead planner isn't just a generic term here.
Right, it has a specific meaning.
Yeah, in the context of Azure AI and LLMops, the lead planner is typically the massive, heavy-lifting large language model, like something like a GPT-4 deployment that handles really complex reasoning and deep logic. It is highly capable, but it's computationally expensive and very susceptible to API timeouts if traffic spikes.
Exactly. So when Margaret says the lead planner vanishes, she's simulating a scenario where that heavy model becomes entirely unresponsive. It just hangs.
Which happens.
It happens all the time. Now, in traditional monolithic software, if the primary database hangs, the user's screen just spins endlessly until it throws a server error. But AI infrastructure requires what we call graceful degradation.
Okay.
So Margaret's hypothesis isn't just that the system won't crash. Her hypothesis dictates a strict performance metric. The fallback architecture must seamlessly route the user's prompt to a different model and deliver a valid response within 3 seconds, preserving that 99.9% accuracy rate.
And here's where it gets really interesting, because that brings us to the psychological shift this requires. Margaret tells Timothy, finding a weakness isn't a failure, it's a win. We find the hole now so we can fix it before the real storm hits.
It's a total paradigm shift.
It really is. Normally in engineering culture, an unexpected outage or a broken build is a really bad day. It triggers incident reports, high-stress debugging sessions, people are sweating. But in a game day scenario, if the monkey breaks the primary API and your fallback fails to catch it, you celebrate.
You celebrate because you just uncovered a hidden vulnerability on your own terms.
Yeah.
You discovered a critical flaw in your architecture while you had the entire team assembled. The blast radius was contained and the kill switch was ready. It transforms failure from a source of massive professional anxiety into a source of actionable intelligence. You're auditing your own resilience.
So the game day plan is signed off. The steady-state hypothesis is totally defined. The team is assembled, and the parameters of the cage are locked in.
The stage is set.
The stage is set. What actually happens when Margaret initiates the experiment?
So this is the narrative climax for Timothy. Margaret executes the script, and the monkey goes to work within its 1% blast radius. The text describes the monkey killing the primary API connection to the lead planner.
Oh, man. And Timothy's just watching that cobalt blue dashboard, entirely tense. I can feel his anxiety. He's just waiting for the latency graphs to spike. He's waiting for the error rates to turn the dashboard red.
But the architecture performs exactly as it was designed to. Rose gives us the mechanical breakdown of the system's self-defense here. First, the circuit breaker trips instantly.
which is a really critical mechanism. For those who don't know, the circuit breaker pattern is a piece of code that acts as a sensor. When it detects that requests to the lead planner are tining out, it immediately severs the connection.
Right.
It stops the system from continuously sending traffic down a broken pipeline, which is what prevents the application from just hanging indefinitely and consuming all available resources.
Exactly. And once the circuit breaker cuts the connection to the failing component, the model ladder catches the weight of the traffic.
Ah, the ladder.
Yes. The primary model is gone, so the architectural logic instantly steps down to the secondary tier. The traffic is seamlessly redirected to the Scout.
And the Scout is the fallback model, right?
Sure.
It's likely a faster, smaller, maybe less nuanced large language model, maybe a localized SLM or a GPT 3.5 instance. It might not have the deep reasoning capabilities of the lead planner, but it is fast, it's highly available, and it's perfectly capable of returning a valid response within that critical 3-second window.
And the routing happens instantaneously. The user traffic flows to the Scout without generating a single failed request. The ladder holds the weight. Timothy watches the metrics and verbalizes his disbelief. He says, the ladder held. It actually held.
The transformation in Timothy at that moment is the core message of Rose's article. He shifts from assumed confidence to earned confidence.
This is beautifully put.
Before the game day, he assumed the system would work because the underlying code was logically sound. After the game day, he knows it works because he has physically watched it absorb a direct hit, trigger its defensive protocols, and maintain a completely seamless user experience.
He has successfully crossed the gap from theoretical resilience to validated survival. He no longer has to rely on hope. He has empirical data proving that the fallbacks execute correctly under pressure. And the psychological relief that provides to an engineering team is immense.
I can imagine.
It allows you to operate without the constant underlying dread of a catastrophic failure because you have already simulated the catastrophe and you survived it.
Margaret caps the cobalt marker, having successfully proved her point. And she delivers the final takeaway of the narrative. She says, the only way to know if your system can survive a crisis is to throw one at it before the real one arrives.
It's an uncompromising standard for reliability. You cannot prove a system is unbreakable by hiding it. You have to expose it to stress.
To summarize the core mechanics from Aaron Rose's deep dive into the Chaos Monkey, chaos engineering is really the practice of building confidence through intentional, highly controlled failure.
Yes.
You protect the production environment by operating within a cage, establishing a strict blast radius, usually around 1% of non-critical traffic. You implement read-only chaos to ensure user data and write paths are never, ever compromised.
Critical step.
You maintain an absolute kill switch to abort the experiment if metrics deviate from the plan. And crucially, you execute this through a formal game day, measuring the system's automated response against a clearly defined steady-state hypothesis.
It's a rigorous framework for ensuring the reliability of complex software architectures. But, while we have discussed this entirely within the context of Azure AI, LLM routing, and cloud infrastructure, the underlying philosophy of validated survival is highly adaptable to pretty much anything.
Oh, totally.
Consider your own organizational structures, your team's communication protocols, or even just your daily operational routines. What would your personal game day look like?
That's a great question.
If you introduced a tiny read-only Chaos Monkey into your own workflows just to see what breaks, what hidden vulnerabilities might you discover before a real crisis hits?
That is definitely something to think about. Thank you for joining us on this deep dive into the world of chaos engineering. Whatever you are building today, remember the lesson of the Victorian library. Trust the ladder you've built, but test it with a monkey on your shoulder. We'll catch you next time.